Hi. So first of all, I'd like to thank Beth for organising this, and also thank you all for coming. I'm going to talk about topology and about how it fits into the history of mathematics. If you look at the Wikipedia page on mathematics, the first thing it says is maths is the abstract study of concepts such as quantity, space, etc. I'm going to tell you what it means by space in the first section. Then that will lead on to the subject of topology itself. And finally, I'll try to tell you what use it might be in the real world. Now, mathematicians have always been interested in space, and for thousands of years, what we meant by space was Euclidean geometry. This is the sort of geometry that you learnt about in school. It involves angles, distances, and all the shapes you can make out of them: triangles, squares, circles, etc. There are 5 basic principles of Euclidean geometry which are considered absolutely fundamentally true, and which everything else could be deduced from. And this was really considered the one true geometry. This is a picture of Isaac Newton doing Euclidean geometry. Now, of those 5 basic principles, the parallel postulate seems a little bit different to the others because it's not quite as obvious. It says that 2 lines that both cross another line at the same angle will never meet, and they stay the same distance apart no matter how far you go, and we call them parallel. This might seem obvious, but it's a bit difficult to check because no one has a piece of paper large enough. Basically, because there isn't a large enough piece of paper, it doesn't count as a proof of this. And for hundreds of years, mathematicians were really worried about this, and we tried to prove it again and again, using the other postulates, but it just didn't work. Eventually, people realized why it hasn't worked. The reason is because it might not be true. For all anyone knows, the parallel lines might actually end up touching in the distance. So this opened up a whole new load of different geometries, the non-Euclidean geometries. So some of them are a bit like living on the surface of a sphere. And so on a sphere, any 2 lines will always meet eventually, because you have to go around the sphere, eventually they'll meet. Other ones are even stranger, hyperbolic geometry, where lines, instead of meeting, they move further and further apart. And this is an Escher drawing, which represents hyperbolic geometry. And you can think of it a little bit like living on the surface of a primrose. Nowadays, we actually know that gravity changes the geometry of the universe, and so the parallel postulate really isn't true. It really is the case that those lines might touch. Anyway, so once mathematicians had realised the old concept of space was far too restrictive, we started thinking, what other ideas of space could there be? What else could we forget about? We could remove the parallel postulate, but could we also take away like other concepts, even the concept of angle and distance themselves? So everyone knows about the London Underground map, and we're all used to using it when we go to London. But what would happen if you used it on the surface? It would really be a disaster, because you would end up going in the wrong direction, you would turn the wrong angle, you'd go the wrong distance, because it doesn't have any idea of what angles are, what distances are, it's all stretched around. So this is what topology is. We throw away the concept of angle and distance, and all we have left is some concepts of like connectedness. So a sphere is called simply connected because it's all one line, basically. There's only one bit. Whereas something like a donut, for instance, is more complicated because if you want to get from one side of the donut to the other side of the donut, then there are 2 distinct ways of doing that. And there's no way of, they're completely fundamentally different ways. Anyway, so here is an interesting topological fact about footballs. If you make a football out of pentagons and hexagons, you will always need exactly 12 pentagons, no matter how many hexagons you use. This might seem bizarre, but I can challenge you, go home and try it. There are lots of different ways. You could use no hexagons. You could use 20 hexagons, like this person's done. You could use hundreds of hexagons, but you're always going to need exactly 12 pentagons. But the really nice thing about this is it only depends on the topology of the sphere. So any other shape of the same topology has this true as well. So a rugby ball is the same as a sphere from the point of view of topology, so this is true of that as well. Even something complicated like a table is really just a sphere from the point of view of topology. So if you build it out of hexagons and pentagons, you would need 12 pentagons. So what use is it? Okay, here's a few applications out of many, many others. In robotics, you want to have a computer program which tells a robot how to get from one point to another. So it needs to choose its path. Some paths are just impossible for topological reasons, and so if you can find a quick way of getting rid of those paths, it makes your program more efficient. In data analysis, with 2-dimensional data, it's easy to look at it and say what the pattern is. But if you have, say, 500 different variables, you have 500-dimensional data, which is just impossible to imagine, let alone see a pattern in. And finally, the example of the football wasn't quite as frivolous as you might think, because there are actually molecules that look like that. And if you know facts about topology, you can use it to rule out certain molecules out without even having to calculate or do any physics. So thank you very much.